This is a tutorial to develop the process generator for arrival times in the Cafe Java case. In this example, we're going to be using a couple of existing packages. We're going to import the numpy package, calling it np, and also import the matplotlib.pyplot package, calling it as plt. Now, in the Cafe Java example, a very knowledgeable customer recognizes that customers arrive at an average rate of about one customer every 2 minutes, or about half a customer per minute. We're going to store this parameter in a variable called lambda and set it equal to 1/2. Again, making sure to use the decimal location to ensure that this is a floating point number and not subject to integer roundoff. Now also in Python, I used the underscore to prefix the word lambda, because lambda itself is actually a keyword reserved for a certain type of functionality in Python. The first task that we have is to create a plot of the PDF and CDF. So that's probability density function and also cumulative distribution function. Now in both of these cases, since we're using a continuous variable, we first want to create an x-coordinate to evaluate these two functions at. I'm going to name these x-coordinates plot underscore x. I'm going to use the numpy.linspace function to generate a linear space between 0 and 10. If I run the script and inspect the plot x, which has been assigned this linear space, we can see that numbers have been generated on an even basis between 0 and 10. This will serve as the points to evaluate the functions and ultimately plot the PDF and CDF. Now for an exponential distribution, such as the case in here for the arrival times, we can assign the PDF values as the functional form of the exponential distribution, which is the arrival rate, lambda, times the exponential function, and using the numpy function for exp for exponential, of negative lambda times the x value. Now I can very simply plot this PDF using the matplotlib command to plot the x-coordinates versus the PDF and very rapidly take a first look at it. And just by its general shape, it appears to be an exponential function, and we can see that this lambda rate is actually the intercept with the y-axis. All right, let's make this plot a little bit better. I'm going to first explicitly call out that this is going to be in a new figure in Matplotlib. I'm also going to give this plot an x label of the inter-arrival time, which is a random variable x, and it's measured in minutes. And the y-axis, I'm going to call little f of x, which is for the probability density function. Okay, looking good. Now of interest, we can actually compare this generated PDF to a built-in function to generate exponential distributions. One that's provided in Python is actually stored within the SciPy stats package. So back up at the top of this file, I'm going to import one more package. Import scipy.stats. And just for short terminology, I'll refer to it as stats. Now in this plot, after plotting our PDF that we generated from the mathematical equation, I'm going to add a new portion to this plot using the same x-coordinates. And instead of using our existing PDF function, I'll use the stats.expon, so for exponential, .pdf function to generate those values. And the PDF we want to generate at those x-coordinates using a scale parameter of 1 over lambda. So sometimes when exponential distributions are defined by a second package, they may refer to a scale parameter which is 1 over lambda. Other times they may refer to a rate parameter, which is usually considered lambda itself. All right, so the second plot I'm going to color as a dashed red line to differentiate it somewhat from this existing PDF. And if we run the script, we can see that those two lines exactly coincide, so we've correctly implemented our functional form for the exponential distribution, and it agrees with the SciPy stats version. So let's try to do the same thing for the cumulative density, or the cumulative distribution function. I'm going to create a new figure for the second plot. And inside of it, we're going to have to first create or evaluate the CDF equation and then plot it. Now in class, we can derive that the CDF for the exponential function is 1 minus the exponential of negative lambda times the x-coordinates. This is actually the simple integral of the PDF function. So knowing that the exponential form stays relatively constant throughout integration and differentiation, we can see a lot of the similarities between these two equations. Now armed with the CDF function, we can again use the Matplotlib to plot the x-coordinates and then the CDF function as the y-coordinates, and set the x label to inter-arrival time, which is our random variable x in minutes, and our y label to big F of x. All right, let's take a look. All right, so our cumulative distribution function is the integral of our probability density function. It starts at 0, ends at 1, and it seems to taper off here as our PDF gains smaller and smaller values. So it looks pretty good. We can again compare this to a built-in CDF function, for example, that in SciPy stats. So I'm just going to add in a second plot here using the same x-coordinates, and then use the stats.exponential.cdf, feeding in the same x-coordinates, and the scale that we used before, 1 over lambda. And again, using the dashed red line. Right. I can see in the second plot that our derived CDF distribution is exactly the same as the one provided by SciPy stats. So it's essentially a form of verification that we've implemented our code correctly. All right, so the next task in this example is to develop a continuous process generator using the inverse transform method. So similar to the demand generator that we performed previously, I'm going to define a new function to generate arrival times. This one is going to be using the IVT method. Now we've actually derived since it's a continuous distribution, we've derived the function that the IVT method can check. This is essentially setting the cumulative distribution function equal to a random number that's generated between 0, 1, and solving for x. Now how that can be implemented here in this function is first generating the random number r using the numpy random.rand function. And then using that solved equation, we can return the transform of this random variable, which comes out to be the log of 1 minus r over that lambda parameter. All right. So similar to the demand generator, we can specify a number of samples, maybe 1,000 of them, and create an array to store these IVT samples. Maybe use the numpy zeros function to start with an empty array of zeros. And then in this case, again, we want to iterate for each of the indices I in the range of the number of samples. For each of the indices, we want to fill the samples in that index with new arrival time generated from this arrival time function. All right, let's give this a quick check to see if everything is working. We can test the generate arrival time function. It appears to give random numbers. They seem the relative right order of magnitude if the average time between customers is about 2 minutes. Or sorry, it's about 2 minutes. We get about half a customer per minute. So the average customer between minutes is about 2. All right. Now we can plot some of these results of these 1,000 queries in the samples IVT. We get a nice array of 1,000 samples using this IVT method. This time I'm going to use a histogram to directly plot the samples rather than counting the frequencies and displaying in a bar chart. So I'm going to generate first a new figure, plot.plt.figure, and then I'm going to use the Matplotlib's hist function to produce a histogram. Now the histogram argument, or the histogram function looks, you can see some of the arguments here. A lot of them are just visual, to change visual elements of it. The first argument is the data that you want to generate a histogram of. In this case, it's the samples IVT. And I'm actually going to choose the bins for this option. I'm going to use bins in the range of 10. So this will create, again, using the bins in the range of 10. Create bins on the points 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right. Can give this a quick shot to plot it. We can see that most of the samples fell between 0 and 1, and then it decreased in a fairly familiar pattern from there. Let's add a little bit more to this plot. Just to keep consistent with the other plots, add a X label, which is the inter-arrival time. These are bins that are being shown on the X-axis in this plot. The units are minutes. And then the Y label in this case is the count, the number of samples that fall within one of these bins. All right, one other thing we can do for this plot is actually to overlay the theoretical distribution from our PDF. So on top of this histogram, just after it in the code, I'm going to create just another plot. And in this plot, I'm going to plot it on the x-axis using our previously generated linear space between 0 and 10. Use the built-in sci-by-stats function, which we used before, to create the theoretical distribution. However, this time we have to multiply the theoretical distribution by the number of samples that we had previously generated so that we are on the same order of magnitude as the histogram counts. So if we run this file, for example, we can now see this theoretical distribution, the PDF of the inter-arrival times that's overlaid, and it matches very well with the sampled results from the IVT method. The last example that we can do is actually overlay an alternative generator. So here we solved the distribution using the inverse transform method, but we can actually use one of the built-in sampling techniques within NumPy to generate random numbers from the exponential distribution. So in this case, I'm going to define a new generator, generate arrival time, but using a built-in NumPy package. In this case, I'm going to just simply return numpy.random.exponential variable, so a variable that's distributed by an exponential function, using that same scale function from before, 1 over lambda. So if I run the script and try calling this function from the console, I'll see that it returns very similar numbers to our inverse transform method that we've developed. and we can add it to the samples that we want to generate out of these 1,000 possible samples. So I'm just going to create a new variable for samples NP, initialize it to zeros in the total number of samples we want to generate. And then inside of this for statement, assign samples for the MP method under index I to generate arrival time using the NP function, the numpy function. And down here, we can add in the plot of the histogram, we can surround the X data, the data that we're plotting in histogram, with square brackets, and add in the second source of samples using this NP method. And if we run the file again, we can now see the blue results correspond to the IVT method, inverse transform method. The green results correspond to the built-in NumPy, exponentially distributed random variables. And the red line is the theoretical PDF of an exponential distribution.